Okay, welcome everyone. We are here. Today as usual Sunday. I hope you can hear me well, and today, yeah, we are doing our regular stream. So topics for today. We will not be solving actually much of LeetCode problems today, unfortunately or fortunately. Yep, let me drop this completely. So I think you might know that I was conducting mock interviews for the people since I was kind of interviewing at Microsoft as an interviewer, and I tried myself as an interviewer for people who need it. So for first four people I did it just for free, just to have an experience, get some feedback. And today, one of the candidates has problems with converting top-down dynamic programming solution to bottom-up. Today, we're going to solve one of the dynamic programming problems, and I will show you how basically you should and you could map top-down to bottom-up. This is exactly the same skill as the skill of LeetCode problems solving. So you just need to practice how to convert these things. And this is how it goes. Later on, after this one, we're gonna continue our system design. In the previous stream, our regular LeetCode / system design stream, we completed monotonic ID generator, scalable one. So today we're gonna start URL shortener system design solution implementation, and maybe we will cover some of the real interview questions. So far that's it. No actual Q&A session. There are no questions so far. I guess, yeah, that's it. So let's start. Let me find the LeetCode problem that we're gonna solve, and I will show you how to proceed with this kind of problems. So good. This is gonna be it. So let me paste it. So the typical stuff. This is the jump game. 55th problem, most probably if you're preparing, you already solved it. If you check the topics, this problem can be solved using three approaches: the greedy and the dynamic programming approach or solution. So the greedy one is not that interesting for us in this case, because we're interested mostly in DP top-down bottom-up approach and how to convert these two between each other. So let's read the problem carefully first. We're given integer array nums, your initial position array index first, and hello, and each element in the array represents your maximum jump length at that position. Return true if you can reach last index, or false otherwise. The greedy solution is not that hard, but again, as I mentioned before, we are aiming to try dynamic programming and then convert it from top down to bottom up. Hello everyone who just came. Hello. Regular Sunday stream, LeetCode and system design. Yeah, get a cup of tea or whatever you're drinking and join. So what it means that actually if let me actually copy this guy here and also put the indices. So this is our jump array, and indices are positions. So at index 0 we have 2. 2 is the maximum length that we can jump from index 0. It means we can jump 0 plus 1 and reach first index, and 0 plus 2 and second index. We cannot reach index 3 because 0 plus 2 cannot be more than 2 or bigger than 2, right? So once we reached first or second, from the first, the maximum jump is 3. So 1 plus 1 is this guy, 1 plus 2 is this guy, and 1 plus 3 is this guy. And fourth index is our last index. It means if we got, or if we reached this index, we are done. We should return true. In this specific example, it can be shown that we cannot reach last index or everything that is after last index. Because at index 0, we can jump 3 steps forward, which is 0 plus 3 equals 3, so this guy. And from the third index, there is no way we can jump because we have maximum 0 jump length, right? So this is it, and how we can solve this problem as in dynamic programming way. So usually, what is the dynamic programming approach? Usually, you can come up with some brute force, which is exponential in a matter of time complexity. Let me also draw you what I mean by that. No, actually, let's not draw yet. So exponential time complexity is the time complexity when our input size, which is n, is inside or as an exponential part of the number. So let's say 2 to the power of n or 7 to the power of n. Actually, any constant to the power of n, where n is our input. This is our guy. So this is exponential time complexity. And why do we want to use dynamic programming is exactly to convert exponential time complexity to polynomial time complexity, which is the time complexity when our input serves as not a constant but as a regular number. So we convert 2 to the power of n to some n to the power of constant, or in otherwise, how can it be stated? Constant to the power of n, we convert to the n to the power of constant, which is much better time complexity. If it's exponential, it's going to grow like this. If it's just n to the power of something, it's I actually don't remember the chart, but it's much better. This is the polynomial, and we always tend to reach to this point. We never want exponential time complexity. This is the dynamic programming kind of background. Now, how I can approach this dynamic programming? First step for the dynamic programming problem is to realize what brute force we can do. In this case, at every single position, so which means at every possible index, we can jump any length from 1 to this value that we have in the array. We can jump any length of the jump. What I mean by that? When we are at index 1, we have 3 options to choose. We can jump 1 plus 1, so jump of length 1. We can jump 1 plus 2, so length of jump will be 2. And we can jump 1 plus 3, which is the maximum one, our boundary, which is gonna be 4. And these 3 choices, we actually don't know which of them is right. So let me draw you maybe another example. Okay. The good example would be at index 0. So we have 2 choices, whether to jump of length 1 or whether to perform jump of length 2. So in case we perform length of jump 2, we reach index 1. And if this guy would be 0, from index 2. From index 2, we cannot reach index 4. There is no way, because we can jump only with the jump with length 1, which lead us to index 3, and from index 3 we cannot jump any further. So jumping just as far as possible is not the solution here. Well, in a greedy one it's kind of the solution, but you should implement it like in a different way. In dynamic programming approach, if we jump from 0 to the farther, which is 2, we cannot reach the last index. But if we jump with length 1 and reach this index, from this index we can jump 3 straight away and reach to the 4, right? LeetCode profile review. Sorry, I'm not getting the question or comment. Like, you would like to see my profile, or should I review some profile? I'm not that good at LeetCode, to be honest. I sold so far 200 and something I sold. This is the amount of problems I solved. Not that many hearts, because I'm not aiming to solve hearts as we are preparing to interview, and bunch of medium problems and bunch of easy problems. So that's it. We had shit. Why it's changing? I don't want to see acceptance. 274 problems solved. If you like to see my profile, this is my profile. I'm not that good at LeetCode, and you can see I started preparing in February, and I keep going so far. So let's see how it will be going. Okay, let's get back to our task. So this is the thing. Since we don't know which jump is better for us and which jump can lead to the end of the array, what we can do, we can actually check every single possible jump. And here is where exponential time starts. Because if we start drawing it, let's say this is index 0. And from index 0 we have two choices. So jump at index 1 and jump at index 2. At index 1 we have three choices, so it's gonna be 1, 2, 3. Jump at index 2, jump at index 3, and jump at index 4, right? 1 plus 3, 4, yes. From this pathway, if we jump straight away to this index, we have only one choice. We can jump to index 3. I think you already got the points that repeat each other. So we have 3 as our input parameter here and bunch of 2s here. So if you have some pretty large input, you will see that you're actually recalculating every time a lot of stuff. But let's not talk about recalculation. Let's just talk about regular hello, what damn. Hello, this is strange, but okay. Didn't I post it in the wrong? Oh shit. Yes, unfortunately I posted in the wrong. I'm sorry, I just need to drop my story. I guess I posted it in my personal Instagram profile. That's why. Yeah, very wrong. I'm sorry. We have 18 people. Oh my god. Yeah, this was supposed to be a story at work profile, not my personal profile and Instagram. So for people who just joined from my personal profile, I'm sorry for wasting your time. Most probably you will not enjoy this stream. Please leave. Okay, I guess I dropped it. So here is some dynamic programming happening. Did I drop it right? I hope so. Very bad, Andrei, very bad. Okay, so yeah, for those who are not interested in solving LeetCode problems in system design, please leave. It was a misunderstanding, but whatever. So let's get back to our dynamic programming problem and solution. So first of all, we are trying to get to some brute force solution, and most probably it will be exponential, which is some constant to the power of n, whereas n is length of our input. In this case, we don't know this constant because constant varies between our values. So I think in worst case, our constant is gonna be this big number, because this is the number of kind of different paths we can take. So in this case, if we have this big number in our array, it means that from our point we would have exactly this number of ways to choose up until we get to the our output and result. So okay, let's say we found our brute force. Let's pretty much implement it right now. I guess we can do it. So far, usually your dynamic programming brute force would look like a recursive function. So for example, let's name it jump or whatever. We have our current index at which we are staying. It can be any index in the array. And our base case in this case would be if index more than or equal than length equals nums length, whatever. Yes, it will be a bit quicker. Which means if our if our previous function led us to index which is more than or equal length minus 1 actually, so we are at that point or any further point, it means that we actually solved our problem because we can reach the last index of the array, and this is pretty cool. Then we return true, basically. Otherwise, if we haven't reached the end of our array, in that case, what we can do? We should actually explore any possible jump that we can do, because any of them can lead us to answer. So if we are at index 1, we're exploring every single possible length of the jump. How are we gonna do it? We're just iterating. Let's name it step. So we're gonna try step 1, and this step should be less than nums index, the particular value, actually less or equal. And step gonna just increase. Now, since we need to explore every single path, we're just gonna call the same function for every possible opportunity, or I don't know, every possible choice. And we're gonna do something like this. So we're trying jump with this particular step length. Then okay, let's name this variable can, and if it's can, we just break straight away. So if we find out that this particular path that we chose led us to the outcome that we can reach the end of the array, we're done. We don't need to explore any further. Now, in case this can, okay, actually we should do it like that. So by default we assume we cannot reach, and if we can, oh sorry, then we just reassign and we break. Yeah, and now what we can do, we just return our can. That's it. That's basically it. I guess it should actually work, and we should return jump from the index 0. So we're trying from our first one, because this is from the description of the problem, right? We explore every single possible jump length that we can do, and if any of them led us to the end of the array, we return true, and it will like return recursively up to the call stack. Let's actually check whether it works or no. It works, but we should get time limit exceeded exception, or not exception, just time limit exceeded. Why? Because what is our time complexity in this case? Our time complexity is very bad. In in this case. Why? Because our input is 10 to the power of 4, and our time complexity is constant to the power of n, actually, because n is going to be maximum length of our array, because these are the maximum steps we can do. So this is the height of this tree, and the height of this tree is going to be n. That's why it's n. And our constant is going to be maximum, in worst case, maximum number of steps we're gonna try. In this case, this is this number. So our time complexity would be O to the power of 10 to the power of 5 to the power, okay. Okay, let me maybe just 1, 2, 3, 4, 5. It's gonna be 100,000 to the power of 10k. Looks pretty bad, I guess. Looks pretty bad. I agree with you. Now what we want to do, we actually want to reverse these two numbers backwards. So O to the power, O to n to the power of some constant. Overall, yeah, this is constant, is like worst case, but overall this is still going to be some constant. Like usually it's gonna be less than this guy. Our main input is still the length of the array. So now this is the time when we can apply dynamic programming to reverse these things. So instead of constant to the power of n, we want to change it to polynomial one, which is n to the power of constant. And we kind of assume that constant gonna be pretty much small one. You're really hardworking. You just earned 1 subscriber and a like. Thank you, thank you, thank you so much. Okay, and now how we're gonna do our dynamic programming. As you can see from my previous kind of drawing or whatever, we can actually explore again, maybe this guy. Yeah, so we are starting at index 0. We can jump 2. So it's gonna be 1 or it's gonna be 2. These are, the numbers are indexes. Indices. From index 1, we can jump, we can explore 3 jumps. So it's gonna be 2, it's gonna be 3, and it's gonna be 4. From index 2, we can only jump 0, 1, 2. We can only jump 1, so it's gonna be 3. From index 3, we can only jump again 1, which leads us to index 4. From index 2, 0, 1, 2, it's again, we already solved it. It is here, by the way. So it's again the same thing, 3 and 4. From index 3, 0, 1, 2, 3, it's again thing that we solved. It's going to be just 4. And if you look at this call stack tree, this is all the recursive functions we're going to explore. Every single node in this tree is our jump function, or sorry, this one. You can see that we have bunch of repetitions. For example, we have bunch of trees over here. So we will recalculate index 3 3 times. We have bunch of 2s, and in the end we reached everything led us to 4. So you can see that we have a bunch of repetitions. I'm not sure why I have 22 people. Usually this is actually this is the misunderstanding, because somehow I posted my story to wrong Instagram channel, and I guess these 20 people is actually from my personal profile. People, please leave. You're not supposed to be here. This is real programming happening here, real programming, so you would not like it. Is it live? Yes, it is live. Yeah. So to eliminate these repetitions, what we can do, we can add memoization. And what memoization means, once we explored one path, and we always gonna explore one path. So actually what's gonna happen from our call stack, if you see this function, since it's not parallel function, we're gonna do everything sequentially. Our first call stack gonna be following this yellow line. So it means once we reach this yellow line, we already know answer for 2, we already know answer for 3, and we already know answer for 4. And it means that these 2, these 3, this 4, this 3, this 4, this 4 is not needed. We don't have to recalculate them every single time. So once we will be at this point, we would return from our call stack back to the 1, and we go to 3, we should already have the result for 3 in our memo. So this is exactly the top-down approach. Once we have this brute force, how to add the top-down? Very easy, very simple. Hello everyone, everyone who just joined. How are we gonna do top-down? Very easy. We're gonna do some memo table. In this case, it can be actually array of lengths, and let's fill it with -1, whatever. -1 is the default value, which means we didn't calculate the answer yet. And top down for dynamic programming is exactly that easy, because once you got a proper brute force, it's very easy to convert it to top down dynamic programming solution. What you can do once you get through the base case, what you are doing is you are checking if memo for index is not equal to -1, which is our default prefilled value. If it's not equal, it means it has answer. We return just this answer straight away. Otherwise, if the answer is not found yet, once we calculated all the paths, we are saving this answer for the later use. As easy as that. And now, what we actually did, we converted our time from constant to the power of n. We converted it to O n to the power of constant. Because now, every single index, so every single, shit, I need to draw it again. Let me draw it again. So now for every single node of our call stack tree, so let's say this guy has 4, this guy has 2, whatever. This guy has just 2. Let's say this is our call stack tree. Now what is going to happen, we're gonna traverse or reach or visit every single node only 2 times. First time it is not calculated, and second time when it's calculated, we're just gonna return results straight away. And that's it. So that's why it's we can worst case assume that we are visiting it only single time. However, it will be more than single time, but at least for this specific call, we are not going to recalculate all the children because we already know the answer. And now exactly same function with just these few lines is going to pass with the test cases. So if we submit, previously it was time limit exceeded. Now we're gonna pass it. Yes, it is very bad still the runtime, but we at least at the boundaries, which is already great. Now the question is how to change it backwards to the bottom up. So this is the top-down approach in dynamic programming. Top-down. We are great. This is the top-down. We use some memo and it is easy. Usually what interviewer will ask you on your real interview at some big tech, okay, but this is the recursive call. And you know the problems with recursion. First, recursion involves method call, which means performance downgrade, because like it's always Okay, not always, it depends on the CPU optimization, but on the raw results, it always worth to do a function call comparing to just have one more iteration, always. And second point, which is even more, even worse, that with your recursive call, you might get stack overflow because your stack is much smaller than your RAM, right? So it's always better to have some iteration. And iteration is exactly possible when we convert top-down to bottom-up. Now, when I was conducting the mock interview, I specifically got this problem that guy was a bit struggling with bottom-up approach. Oh, sorry, converting top-down to bottom-up. How usually you convert top-down to bottom-up? Explaining. Let's draw our call tree again. So, we're starting at index 0. Sorry, let's do red one. We're starting at index 0. Then we can jump either to index 1 or to index 2. From index 1, we can jump to index 2, 3, 4. From index 0, 1, 2, we can jump to index 3. From index 3, 0, 1, 2, 3, we can jump to index 4. From index 4, we know it's already answer. And the same thing for index 2 here. Exactly. This is our call stack tree. Now let's imagine how it will be executed. So we are entering the function jump. It starts from index 0 and it calls itself again. So we will try from the lowest possible value. So we try with step 1, +1. And let's also record our call stack. So we go here. Then at index 1, we again here, this is false, this is false. We again try in step 1, the smallest one, and we go to this guy. So exactly the least possible one. At index 2, it is exactly the same thing. This is false, this is false. We are trying from the lowest one. Again, a recursive function call. And same thing will happen with index 3. We go to the 4. In this case, this guy will be true, it returns back, and here we are. This can gonna be true, and we're gonna break it. So we return true here, we return true here, we return true here to the 1. Now we are at index 1, and we already kinda no answer for 2, no answer for 3, no answer for 4. Now we're gonna try step 2 and go to the index 3, and this guy gonna be solved already. Then we're gonna go back to index 4, this guy gonna be solved as well. Yeah, actually, I'm sorry, in our algo we are not even going to try these guys because this call return true, so we just return true here, and that's it, we are done. We will not even explore this array. Right? Yes, because of this break. In worst case, if we remove this break and we do this, then yeah, we're gonna explore and just return straight away because we already know answer for these guys because it was calculated during the first traversal. Let's even try. Yeah, and we are hitting our time limit exceeded. Even memo is not helping here, unfortunately, because we are going to traverse everything, right? How to convert it to bottom-up? Exactly same approach. You just need to follow your real program execution and do it and reverse it. So top-down is exactly called top-down because we're starting from the top of the tree and moving to the bottom. Now instead of starting from the top of the tree, you should start from the bottom of the tree, which means 4. And 4 is our base case. We know that we can set true in our memo for the index 4 and all other indexes that are bigger than 4. So I'm leaving this function as it is, and I'm just trying and straight away gonna convert this function to bottom-up approach. So our base case, oh sorry, actually, yeah, whatever, HGS is dynamically typed, so we can do this. This is our base case. Now, since it's bottom-up, we are kinda going from the bottom to the up of the call stack in this direction. Next one is going to be tree. What is important here, that since we are going from bottom up, we always should reuse somehow previously calculated values, which means we should go from 4 up to the 1 in our indexing or in our iteration, whatever you call it. So now we can start from index 3. I'm exactly doing this thing. So we have some index I, whatever it is. We are starting length minus 2. Why? Because we already executed stuff for length minus 1. So we're starting length minus 2. So let's say we have our memo. This guy is already solved. We are starting from this guy. And we're going to traverse it backwards. Exactly like in our call stack here. We are performing it up until I is bigger or equal than 0, I minus 1. So we are just traversing backwards in our memo. Now, for every single memo, how are we going to calculate it? The safest approach is just check of your top-down function. Just check it, how it works. And this is the base case. Base case we don't even care because we will not have it. Or we will have it, whatever. This is our like the body of our function, right? This is what we are doing. We are calling this jam, and let's just, let's just copy it. I'm just copying it from top down. We can have our can equals to false. We are trying every single step. Our index in this case is going to be this one. So let's change I to index. So even variables are the same. Everything is the same. Now, since we know that we cannot call our function, instead it should be memo that we already actually it should be this. Previous method version was this. So now instead of this guy, how we changed it? We are writing can equal to our memo index plus step. So exactly the same, but instead of calling the function, we are going to our memo array and trying to get value from here. But of course, it can be this index can be larger than length. And this is our this based case, and we're gonna actually check it. So let our I or whatever, if this I is more than or equal to, oh wait a bit, I can even rewrite it in different way. So our can, in case it's indexed like this, okay, anyway, let's do it like this. So let's name it jump index. So if our jump index is more than or equal length minus 1, can should be true. So we can reach it, right? We're gonna return true. If not, we just check what is in our memo that we already pre-computed, because we know it is in boundary of memory array, and we assign it to can. Now, if can is true, we just break, and we're exactly doing same thing. We are setting the value for our current traversal to whatever we calculated for can. So our memo, our index equals to can. And in the end, we just return memo from 0. Exactly. So let's actually try to call this function. Top-down approach we don't use, I just leave it for the reference, right? Let's check whether it works or not. It works. Let's check. Yeah, performance it's a bit better than top-down because of unnecessary function calls and whatever I said to you. And let's now compare the top-down and bottom-up and see how they are actually similar. So I'm going to do it in my Visual Studio Code. New file. Oh, whatever, please give me a new file, thank you. And shut up. Okay. This is our top-down approach, and we can see it on the left side on our screen, and this is our bottom-up approach. As you can see, they are actually very similar. So when you're converting them, you should first of all think of your call stack and try to implement your call stack from the reversed order. So starting from the base case and moving up to the start of your input. Next stuff, to simplify your life, instead of designing the body of your iteration on your own, you can just copy paste it from your top-down approach. So in this case, this is my body, right? So I'm setting variable can, and I'm calculating this variable by calling subsequent possible jumps, you know. So this is, I literally commented this code out. The only thing we should add that this base case, if index is more than length minus 1, more than or equal, then we already say it's true and we return it true. And this is kinda implemented here. Everything else is exactly the same. Instead of recursive function call, we are calling and asking our memo array. So eliminating this recursive call. And now with converting it to bottom up, it's quite easier to analyze the time complexity than time complexity of recursion. Time complexity of recursion is always harder. Why I prefer to resolve LeetCode tasks in JavaScript and not on C#? It's much quicker, and sometimes you are missing something in C#, so you have more syntax errors. Also, array initializing is much better with JS. However, in new C#, you also can do like this. But LeetCode doesn't use new C#, so you end up doing like proper new blah blah blah. So I don't really like writing in C#. I'm using C# whenever I need optimized queue for constant type and priority queue. In this case, C# is you can automate it. Also, if I want to solve something in C# and I don't know the interface and basically signature of the method, I should go to Visual Studio, try it, or like look up the documentation. In case of JS, what I can do this, and let's say I don't know how to split array or whatever. I am straight away doing like split, and I see what's gonna be the result. Oh shit, split is not function. Okay, whatever, I can do it like that, right? It's for string, I'm sorry. And I can see what will be the output, right? In different cases. And this is how I test. I don't need to open any IDE. I just F12 and test whatever I need to test. That's why JS. However, my main language is .NET. I'm writing the backend all my life in .NET. Come on. Yep. So now time complexity is much easier to analyze in bottom up because you see 2 for loops. You know what can be the biggest value in the value of nums, which is this guy. Sorry, this guy, and you know what can be the largest value of the length. And this is exactly how you can easily calculate the time complexity with bottom-up approach. Bottom-up approach usually converts also to even more simplification, because now you have your memo, so your complexity is gonna be some constant to the power, n to the power of some constant, plus for space complexity is gonna be O of n, because our length of our array is actually length of our input. But then bottom-up approach also can be simplified to constant space. Instead of memo, you're kind of reusing your previous variable. I'm not gonna do it today. This can be homework. Not all dynamic programming tasks are supposed to have this optimization, but just for you to know that step 4 is to convert it to constant space, and then you will have just, you know, polynomial time complexity. That's it. I think we are done with this dynamic programming stuff. Now for our agenda, we're going to change our topic to system design. Let's, okay, this is for my videos and articles, which is coming soon. Okay, this one actually was already published. About backend versus front-end complexities. Some people claim that front-end is harder than backend. Well, okay, what are your thoughts on overemployment? I don't think overemployment is a thing right now, because COVID times are gone and there were already a bunch of layoffs for big tech companies 2 years ago, I guess. Like this, you remember, I guess you all remember that Google laid off like 10K, then Microsoft laid off 10K, then Meta laid off 10K, and there were a lot of 10Ks people laid off. And I don't think there is overemployment. The only one overemployment that can come is due to AI, but usually for smaller companies, because bigger companies and larger projects, they will never replace their employees for AI, because they value reputation more than this 2-3K, 4, 5, 6K per employee, right? So I'm not sure about overemployment. The thing is that maybe market is a bit less, how to say, eager to get you comparing to COVID times, right? Because yeah, nowadays it's quite harder to get the job comparing to COVID times. That's true. But I don't think there is overemployment. There is undersupply of the market. This is true. Yeah, this is true, because companies don't have that much money than they had before. Only maybe AI companies have some additional money, because investors right now are like doing this bubble from money for AI companies, but AI companies are still very hard to get to, because usually they require a PhD in AI area, right? Which usually people don't have. At least I think I have bachelor and masters in software engineer, but not in AI, and I don't have PhD. So, yeah. In short, yeah, nowadays it's much harder to get the job comparing to COVID times. Maybe comparing to before, I don't know. What are your resources to learn system design? Okay, pretty frequently asked questions. So I'm asking system design questions and try to build it on my own with whatever I know now, and then I'm just reviewing 2-3 more same system design questions solved in YouTube or whenever else. That's how I learn. Also, you need to read Designing Data Intensive Applications by Martin Kleppmann. This book, like, this is top 1 for your system design. If you didn't read it, don't even try and don't even start doing system design. This book has fundamentals that you will require for your system design. Well, this one, also lectures from Martin Kleppmann are very important to watch, and that's it. And then you can just try your system design and apply patterns you already know. There are a bunch of other books, but they are rather optional than required. For example, software architecture in practice, or how it's called, software architecture in practice by Kazman. Rick Kazman, yeah. So this book, it is also quite cool. The thing is that it is a bit boring, I would say. It's not that exciting in designing data-intensive applications, so you might have a lot of motivation to read it, but this book contains a bunch of patterns that you can just blindly apply, and you know they will work. For example, okay, you have some high availability, you use replication. If you have a replication of stateless, you use this. If you need a replication of stateful, you use this. But all the pitfalls, all the interesting stuff about replication, partitions, and stuff like that, it is in designing data intensive. It's in Martin Kleppmann's book anyway. So I would say the only required stuff for system design is designing data intensive applications by Kleppmann, and that's it. You don't need anything else. You can still do a good and solid system design solutions only with this book and practice. Okay, so where we stopped at previous time, we implemented and load tested Snowflake, which is a scalable auto increment solution. What we're gonna do today, I don't think we have much time. Maybe we can just set up project and stuff like that. We're gonna do URL shortener. So we, like bunch of streams ago, what we decided that the most optimal solution for a URL shortener is this one. So we need numbered unique key, and from this key, using base 62 encoding, we're generating a small sequence of symbols, and this short sequence of symbols we're gonna use for our URL shortener, and then just resolve the URL and redirect the client. Basically, this would be our way, and this will be a cool part because we're gonna actually combine two system designs. First one is scalable unique ID generator, and second one is URL shortener, which that is going to call our Snowflake auto increment solution. So first of all, okay, this is memory link. This is for later. Now this guy is changed to milliseconds. It was for load testing purpose before. Also, what we're gonna do, it was also for purpose of load testing to verify correctness. Yeah, basically we can command hold this method. Yeah, this was for verifying of the correctness. In a nutshell, our code should look like this. Yeah, so we are taking the Snowflake approach is actually scalable, unique numbered ID generator, which is also kind of monotonically increasing. It is working using same mechanism as universal IDs, so QUID, or unique universal IDs, yes. So we're taking milliseconds, sequence number, machine ID, and then we are shifting the bits. So the whole number represents all of three such parts, and they are guaranteed to be unique if we have unique machine ID. That's it. And sequence ID is atomically auto-incremented seen per machine ID. So it will never be same. We implemented it using interlock increment, which guarantees that it will use specific CPU instruction and do atomic increment under high load and concurrent circumstances. Now, what I'm gonna do now, let me actually open, yeah, LeetCode is done. We had a Docker file here. This was for snowflake auto increment, exactly. And exactly same thing we're gonna create for URL shortener. So let's just do it. Please, let's set up project and let's create client for our auto increment. Maybe Dockerize it as well. So we're gonna have new solution. It's gonna be URL shortener. Oh, shit. Regarding the projects, it's gonna be projects, distributed systems. This guy, yes. Git is already created. .NET 8 console app. No, it's gonna be web, and it's gonna be web API. Yes, just API, not module controller, not Razor pages, exactly. Syndication, Docker support we don't have. We will copy paste from previous solutions, and that's, I guess, it. Let's create it. I guess I can actually write what we are doing. Properties. Can I do like this? No, it looks very ugly. Maybe here I can have it, yes. This window, yes, exactly this window. Okay, cool. This is our URL shortener. Weather forecast we don't care. So what our URL shortener should have? It should have, let me think of API. So it definitely should have redirect API followed by our short URL sequence of numbers. It should have API for creation of this API, and I would say maybe for deletion, but it will be for later. So first of all, let's do map create. Oh, sorry, not create. Come on, map post URL. Do you want to create vice versa thing? Nice. I have subscription. Whoever just subscribed, thank you on Twitch. Welcome to the channel. Now, do you want it to be actually? I mean, how I can get this number? So, let's say we have URL endpoint, and this is gonna be post. It has input URL, and it gives you as an output short URL. What if I lose this short URL? Can I somehow query it back? Well, actually, in reality, most probably I will have some authentication, authorization, right? And I will have only access to my created URL, so we can just show all the URLs of this specific user. In our case, we are not going to bother ourselves with the authorization and authentication. So let's say we're going to have just get method for URLs, which is going to show all of the URL, short URL, long URL mapping. And we're gonna have maybe delete, but delete I don't think we need for this MVP, and post for creation. Yeah, that's it. So first of all, we're gonna have this method, and I guess we need to create some client. We're gonna have some client that will query unique ID, and this is what what we're gonna start with. So unique ID client. Yeah, let's name it like that. And here we would need private read-only HTTP client factory. Okay, this guy needs exactly, and what we want here is this guy to return long. It's gonna be 64 bits, get unique ID async. Thank you, Copilot. It is pretty handful, but one thing, you don't dispose the stuff. This is very bad. Anything of this, wait, no, this guy, no. Good. Now, how we're gonna call it? First of all, we need some URL. So Snowflake. We need to connect our Snowflake URL, and we're gonna connect them somehow. For now, let's put HTTP localhost, and which port does it have? Let me check. So our Snowflake is configured, I guess, in program, not here in Docker Compose. Then, okay, we don't need this thing. Okay, we actually can have 2 instances, no problem. But then we have load balancer, and load balancer has port 5000. So this is exactly what we're gonna put. 5000. This is our Snowflake base URL. And now what we're gonna do, let's not bother ourselves with options pattern, this I options for .NET guys, you know. Let's just put straight away I configuration. Yes, exactly. And now our base, or maybe not this guy, create client name, just create me random client and get async. What I'm gonna do, I want to combine it. So configuration get value string, it is named Snowflake URL. Yeah, and what is the endpoint in our case? Identifier get request. This is identifier, so let me just copy it. Get async, and response should be successful status code. Read a string and long. Yeah, exactly. I don't like this kind of ifs. Also, base exceptions are not that great. Don't do this. I think this should be enough. This should be actually enough. Yes. Now I should register a bunch of stuff. So first of all, we should register builder add HTTP client. No, just add HTTP client. And that's it. Then we're gonna add our client. Should it be singleton or transient or whatever? Let's think about lifetime of our service. It doesn't matter. Let's add transient. We don't care basically. Unique ID client. Exactly. Now we're gonna inject this guy here. Unique client ID equals await client. This guy should be async actually. And we're gonna just return ID just to check it works. Good. Let me, one more thing for Docker support later on. We would need, let me show you which one exactly. We would need this guy before Swagger. This is internal Docker port that we're gonna map to whatever we want. This is needed for different stuff. And now, let me first of all try to run this guy and see if it works at all. If it works, we're gonna do, we're gonna just add Docker support and that's it. Okay, I need to ban one guy in Twitch. Hello. Let me ban one guy from the Twitch. Additional. Here, how do people set? Yes, perfect. Okay, now. Yeah, let's actually check it. It should be 80 port. Yep, it works. But now it should throw us exception that it cannot actually resolve. Yeah, it's gonna be timeout because it cannot reach our Snowflake, so unique generator, system design implementation, you cannot reach it. Therefore, what we're gonna do, let's Dockerize it. Shit. Yeah, let's Dockerize current solution. How we're gonna do it? Copy paste. I'm always doing. Okay. So first of all, we would need. Yeah, let's do it proper way. SRC folder. And we're gonna put everything here. And also git ignore as well. And also this guy as well. Also we are doing load tests for later. And then we just copy paste in Docker compose Docker file. And now what we should do, we should change here simple stuff. So oh, sorry. Since I have Vim, I cannot do it, or what? It's actually bad. So we're gonna change Snowflake auto increment to our another folder, which is called URL Shortener. Just like that. Now let's try to search Snowflake. Nothing. Good. So Docker file is changed successfully. Now we need, please follow. Yes, good. Now let's first start with URL shortener. Load balancer for Redis, we don't need Redis. And now this is the tricky part, because if you have two Docker Compose files, they cannot actually reach each other because they are under different private networks. Whenever you do Docker Compose up, it creates a private network, and only services which is inside this Docker Compose can access each other. Services that are up from another Docker Compose cannot interoperate. That's why we are putting we're gonna call this network as a system design network. And we're gonna now put this network everywhere. Also everywhere in here. Yeah, and since this network is gonna be external, we have to create it right now. And I don't think we need two load balancers. I actually think we need only one. And actually, it would be great to have it in a separate folder, but. Actually, in a sense, I think it should be URL shortener load balancer, to be honest. Server. Shit. This is now interesting how we're gonna do it. Okay, let me do it in a stupid way. So we are putting URL shortener here, also port 80. Now let's just put this guy. This is Nginx. This is already something that usually you will not use Nginx. I guess in a real production scenario. But I had a bit of experience with this, so I kinda know. And now load balancer Nginx is good. It is there, volumes are passed. Good. Good. Now what we have to do, Docker network create system design. Perfect. Now I'm gonna go to URL shortener, do Docker compose up. Okay, and now we're gonna. Yes, sorry, I think this is what we need to do. Now we have actually two panes. One's gonna be for our sub-service, downstream service, which is Snowflake increment. Let's first Docker compose up it. I removed the load balancer because we don't actually need load balancer anymore. Our load balancer will be in downstream service called URL shortener. Snowflake auto increment is only our kinda Yeah, downstream service client. Plugin external not found. Okay, let's just check it. Come on. Docker compose external network has. Is it Russian? No, it's Ukrainian. Okay, actually it should be just external true. It should be name. Networks, network 1. Do we need name at all? I don't think we need name. Let's just try with this guy. Yes. And exactly, let's try again. Good, we are up and running, but this is only Snowflake. Now what we should do, we should also set up our URL shortener. It's building for the first time. Also, I'm gonna monitor what do we have in a separate CMD. So yeah, we have our Snowflake up, Redis, and another instance of Snowflake for the balancing. Okay, it was set up as well, which is pretty impressive. Now, how do we call it? Our URL shortener has just internal port 80. It's not exposed to external world, but we have load balancer, which is exposing 500, and this is its config. And configuration has shortener backend, which is this guy, which calls this internal local port. So it should be localhost shortener Swagger, I guess. So let's try localhost shortener. I'm sorry guys, need to sneeze. Okay. So shortener Swagger should work with. No, it doesn't. Fuck it. Just Swagger. Just Swagger works. But this Swagger works for okay, I'm gonna ask it in GPT, I'm sorry. I don't really remember how it works, but yeah, let's just feed it. How can I access? Do I have it up and running at all? URL shortener 1. Oh yeah, by the way, it should be up and running. Okay, somehow it doesn't work. Let's actually check the logs of Nginx. Why can't resolve it? Just for all 4. maybe the order of the rules. Okay, let's try this response, whatever. So we should actually do this. Yeah, some Nginx magic, don't even ask this, just do whatever it suggests, because yeah, Nginx is usually magic. Let's just try to Docker compose up. Oh, sorry. Let's maybe do this rebuild. Okay, it is attaching. Let's try again. Okay, now it works. Perfect. Now I want to see whether our stuff would work. It will not work. Let me understand why. Well, yeah, I can't understand why, because we didn't override our configuration. And I'm gonna do it just now. Okay, we have it already. So, what should be our base URL in this case? Our base URL should be our I should reopen it. Yeah, URL shortener. SRC URL shortener. Transform. So it should be Snowflake base URL, and it should go load balancer. So let's just copy paste it. And do we need port? I don't actually think so. Maybe let's try without port first. Not found, right? What is in the logs in our URL shortener? Ah, shit. It's not found by... Yeah, it's not found, and I know the reason why it's not found, so we gotta use something else. Do I have Postman? I do. Which is nice. I will explain the problem. So Swagger tries to send this URL, which is not correct because, well, our, how to say, our URL shortener is configured to be under specific path, so it won't work. Come on, please load Postman. So I just want to remove everything I had. Okay, and now we're adding the guy. We're getting post shortener URL. Okay, nice. It works. It works. So take a look. I will explain you what is our flow. I'll maybe even write to you. Sorry, draw for you. So how it works at the moment, we have system design. We have system design. Oh, I can draw even here, right? So we are designing URL shortener, and we already gonna use Snowflake auto increment ID generator, which is scalable number ID generator. How it works? So we have our URL shortener, which is exposed by local URL shortener 80. This is internal Docker host. We also have a Snowflake IP, which is exposed something like Snowflake. This is internal Docker host. Also, we have load balancer, which is Nginx. Nginx, which is our load balancer, but not API, but 5000 external port. And this guy knows about two of these. So that's how actually Snowflake is, URL shortener is asking for the unique ID generator. It basically asks it through this Nginx, who is redirecting it to this Snowflake. And this is inside one big Docker network called, I will tell you now how exactly it's called. It's called system design. This is the big network. This is how it's locally working. They can access each other by just the name of the container in Docker, right? And how it works logically, that now we have, I actually don't need these guys. So how it works logically, that we have our URL shortener. We are asking this URL shortener to return us URL. Under hood, how it works, that URL shortener is just asking Snowflake to get a new identifier and just returns it like that. So just like that, we have created, it asks for ID, and it returns ID backwards. In the next system design stream and LeetCode, we're gonna implement it further. So URL shortener gonna convert it through the base 62 to some sequence, and then we will see later on. We're gonna do system design first of all without implementation, then we're gonna implement it. How this sequence is gonna be stored and how later on it will be redirected to the source URL that the customer asked us to redirect to. Okay, I guess that was it. There will not be a Q&A session because we don't need to, and we don't have any questions so far. Real interview questions, this outsource things we are not going to do today. I think we streamed enough. So thank you for your attention. It was me, Andriy, and see you next stream, next Sunday here at Microsoft Office again. Bye bye.